That is fantastic. Should have done a bowl.
Which microphone?
Hello, everyone, and thank you for coming in a bit early for the Traffic Corner Tuesday. We will go ahead and get started here at the 12:30 mark. Once again, I want to thank you for coming in early and for attending Traffic Corner Tuesday. Hello everyone, I want to thank you for coming in a little bit early, starting with chapter 2. I just opened up the polls, so I'm continuing away with my schedule set out, but still looking for that. They will be starting at 12:30, and I'm going to the chat box. The questions and so, and thank you for your questions, answers, comments out there, and we'll starting promptly. Hello, everyone, and welcome to Traffic Corner Tuesday. My name is Paul Kerr, a Client Relationship Manager at SPAC Enterprise, and I'm your host for today's webinar. If you've attended our webinars before, you know we view safety as a primary concern and continually try to improve how we complete our work accordingly. We have learned, as we've learned, sight distance falls into that category and has become a key part of our transportation studies. Today, Mike and Brian will discuss sight distance and how it relates to our work. However, we want you to join the conversation by using the chat box on your screen to ask questions or share your experience throughout the presentation. We will try to work your comments in as we go and also do a Q&A at the end of the presentation. You can always email Mike or myself as well if you think of questions later. The Traffic Corner Tuesday webinar series is brought to you by SPAC Consulting, which is part of the SPAC family of companies. SPAC Enterprise consists of a group of traffic engineering companies focused on helping you create healthy transportation systems and fix broken ones. Please visit our website, spacconsulting.com or countingcars.com to learn more about us and schedule your consult call. From transportation equipment to traffic counting to engineering studies, we're here to help you succeed. Today's presenters are Mike Spack and Brian Fiesek. Mike is the founder and CEO, while Brian is the president. Both believe strongly in improving transportation globally, which includes these webinars and other types of dialogues with colleagues and government officials. As licensed professional engineers and certified professional traffic operations engineers, they recognize their impact on families across the world. Through their and the entire company's work, they're saving lives and reducing congestion every day. Mike and Brian, please take it away.
Thanks, Paul.
All right, thank you, Paul.
Let's dive in. And this topic is close to my heart in that I first dealt with a painful situation when I was the traffic engineer for the city of Maple Grove, a suburb here of Minneapolis, early in my career, where we built a main street in the suburbs in an old gravel pit. And the way the parking was laid out and the buildings were laid out, it was really hard to see at the different intersections along Main Street. And kind of the light bulb went off of, okay, it's Main Street, that's okay, traffic should be slower, but it went a little bit too far. And since that experience, I've been really sensitive to, can we see when we get up to an intersection?
So what we're going to show here are just some random pictures. You can find them throughout the country, throughout the world. I mean, everywhere. It's just sight distance issues are too common. So you pull up to your intersection, you're trying to look for oncoming traffic. You've got trees there or something else. On this overhead one, you can see intersections at a skew. What happens if you're thinking about the future there and you add that fourth leg? How does that intersection work today? How's it going to work into the future?
Then I wish this was laughably uncommon, but I saw one of these this week. Again, it's just too easy, especially with the vegetation, that things grow, and we don't have a process and a system out there for staying ahead of it.
There's another one with not only the vegetation, but this one has the retaining wall by it too, that as you're trying to look over there and you're sitting in your car, you don't have the height to look over that. This can be common in our area. Some areas not so much, but as you get the snow built up, as cars park, as they move further away from the curb and out into the street, you start losing your sight distance there too.
And then another area with just a lot more trees and shrubs and things at the intersection.
And right at the corners that you're trying to look through. And then again, just common issue, blocking your sights there. Final one is you get development and they want to mark out where they are, and they put this nice sign up and it's right exactly in the wrong spot. And now you're trying to look through a monument while you're trying to move out into the public road. So all very common items. I'm sure everyone can relate with these types of pictures. And what we have found is that your typical study is focused on the cars and the operations, level of service. Are we gonna add a turn lane or not? Which is all good things you should be looking at, but sight distance, even if it's recommended in some of our guides, doesn't always get added in. It's more commonly in a safety study, something like that.
Which is after the fact. It's being reactive instead of this great opportunity for us to be proactive.
So what we're gonna start with are just the different types of sight distance. So first one we have here, stopping sight distance. You're driving along, you see something in your way, and your stopping sight distance is you've detected it. You have this time in the green arrow there, your reaction time, you're recognizing what's ahead of you and what you should do, what action you need to take. So after a bit of time, you hit the brakes, your car is braking and the vehicle stops, and that's basically those two combinations. There's your stop and sight distance. So common for roadway design, roadway construction, typically would not be part of your transportation study. This is kind of outside, it's part, like I said, of that design of a road itself. Next one, somewhat related, is decision sight distance. And this one, rather than just the stopping sight distance, something unexpected comes up. Hey, look at that, a dinosaur. That would be unexpected. And what that means is your reaction time has increased that much. It takes a while for it to actually register in your brain. You're looking at it and going, oh my gosh, what is this? What do I need to do? And so that increases that reaction time. There we go. Then you're hitting the brakes like before, your vehicle is braking and stopping like before, but the combination is that decision sight distance, longer than stopping sight distance, but again, an element that isn't typically part of their transportation study, wouldn't be something we would normally look at.
And here's the next one that also wouldn't be part of a transportation study for a neighborhood or a development, but also an important part of our engineering toolbox when we're looking at safety and looking at redesigning roads. It's, you have one car coming up to a slow moving car, you're in a zone where you can pass. You hope the vehicles are going about the speed limit because that's part of the engineering calculation.
Yep.
And then we get into the time for the person to decide and then overcome the vehicle and get back around them.
Safely move back before something bad happens. So like Mike said, again, not part of what we would typically look at in our studies.
Okay. So we're finally getting to what we should look at in our studies. And this is the intersection sight distance. And AASHTO, the Green Book, and in a lot of the state design manuals that adopt that, we get into different cases. They're called in the jargon, but they're just different situations, and it's describing the intersection, traffic control.
So we've laid them all out here. Case A, no control, no stop signs or anything. It's just an intersection that you come up and you need to be aware of traffic around it. It's up to you to decide what to do at that intersection. Case B, more typical, is side street stop. Just one street stops, the other is through traffic. Very similar. Case C with your side street yield. And then you move on to the higher levels of control. Signal, always stop, and then a new one in the new Green Book is lefts from the major road. So it could be at a side street stop again, but as you're looking at oncoming traffic and trying to make sure you have enough distance to make the decision to go and take that left turn. Finally, roundabouts. So all different cases, these are all dealt with in the Green Book. They show different distances and how to treat all of them. But really, for our studies, what it comes down to and what our focus is on that side street stop. And similarly into that side street yield, but most importantly, we feel this is the side street stop is going to be your most common intersection, whether it's coming out of a driveway, an adjacent intersection. That's the one that matters.
We should throw in the caveat that That's for sure in the higher speed areas. Now, if you're a city, you have hopefully have a whole lot of neighborhood intersections with no control. At least that's my leaning is I'm a minimalist when it comes to signs in neighborhoods because we have rules of the road to deal with it. But we need to deal with sight distance there. And a stop sign can be part of the solution if there's limited sight distance.
Have a reason for putting the stop sign up though.
Yes.
And we had another webinar about using yields as well, compliance at stop signs. You can try to look that up. And basically, we feel we don't use yield signs enough.
But the public treats neighborhood stop signs like yield signs.
Right.
Which is
Look for that other webinar there, but again, what we're going to focus on right now is that side street stop and how we look at it. And again, particularly if you're looking at a development, this would be your driveway coming out onto the public road. They have to stop, they need to look for traffic. So some of the key components of this and what we're going to be looking at, and again, you can go to the Green Book, all this stuff is in there, presented in much greater detail, but we'll give you the basics here. As you're looking at things, your height of eye is 3.5 feet. So that's sitting in your car. You're not fully standing up. Obviously, you're down lower, and that's about where your eye is. A truck would be higher, obviously.
Yeah, you're sitting in a sedan, not a Suburban.
Correct. But that's the starting point for where they want your height of eye. Height of the object that you're looking to, also 3.5. So that is, as you're looking down the road, that's what you're trying to see.
So you're trying to see another vehicle, pedestrian, bicycle, something
coming
moving at you,
Yep.
not roadkill that's laying at a few inches off the
Yep.
ground.
And then this next one that popped up, minimum 4.5 feet, that is the distance from the travel way back to where the driver is sitting. That's the minimum distance they recommend, which accounts
And
for
14.5,
I'm
14
sorry.
and a half feet.
14 and a half.
So that accounts for the hood of the vehicle not quite pulling into the intersection.
Little distance from where the cars are traveling and the hood, like Mike said. So the minimum 14.5, as I correct myself, that can be more, and there are some places, or there are some recommendations that say you should go a little bit more than that, but start at that for sure and see if you can at least achieve it there. And then obviously from that standpoint in the vehicle, you're looking to either side of where, how far you can see down the road and what that is. And we put the basic formula there. ISD, intersection sight distance, equals 1.47, which is just a conversion factor, times your speed, which is typically your posted speed. So in our example here, we have it at 40 miles an hour. So you put 40
This
miles
is
an hour.
imperial units.
Yep.
That's what this factor applies to.
Yep.
So if you're in the UK, adjust appropriately.
And then the last one, T, is for time. And for the left turn movement for the stop sign, you want 7.5 seconds. So that's what the research has shown you need to achieve your turn and get up to speed so you don't get rear-ended by the vehicle behind you as well. For right turns, it's a little less, but at your typical four-legged intersection, a little different than what we have T shown here, but at your typical four-legged intersection, you want to achieve that 7.5 each way. Just you've covered all movements in that case. Your left turn, you're through, and your right turn from both sides.
So you multiply the numbers out, 1.47 times 40 times 7.5, you end up with about 445 feet. So on a 40 mile an hour road, you need about 450 feet. If we plug 30 miles an hour in there instead of 40, a more urban condition, then you're down to 330 feet. So you can see it's sensitive to the speed limit.
Very much so. So those are the basics of how we look at, or how you can measure that sight distance, the different components you're looking at. Now what we want to go into is how we look at it when we're doing our studies. And we have two different methods. So the first one is just measuring it on paper. We have a site plan, something similar to what's shown here. You can take that and with a ruler very easily start measuring that out, assuming everything's to scale, obviously. Again, if we assume our road here, use our intersection site distance formula, 35-mile-per-hour road, 7.5 seconds, we get to 390, 400 feet is what we're looking for. And so we would then take that on our aerial, measure our distance back from the road.
Yep, moving back 14.5 feet.
Yep. And in this case, our dot there is in the left turn lane, trying to get close to where that driver is sitting as they're waiting to make that turn. And then you draw the straight edge back each way. And can they achieve that about 400 feet each way? And so in this particular instance, you can see to the left side of the drawing, plenty of sight distance all the way through. They can clearly see the cars coming from that direction. As you're looking the other way, you start to get close to those landscape trees in that median between, in this case, it was a school, between that bus drop off there and the public road. So that might be something we would look at then. What is the plan for those trees? What's the canopy gonna look like? Maybe we should move them back a little bit, try to get them closer into the development, closer to that bus drop off area, farther from the public road.
Right, and a couple clarifications, the 390 feet is seeing along the hypotenuse of the triangle. So it's actually a line of sight, to clarify that. And another level of this is also getting your hands on the survey if you're in an area that has rolling topography, that you also need to plot this out on the vertical curves. So you can check as well that site distance isn't going to be blocked by a hill going away from you. And that typically not an issue, but a small fraction of our studies are along roadways that are hilly.
Yep, and it's another aspect to account for. In this particular study, it was flat area, so we didn't have to worry about that. Given the time we have, we want to make sure we could show you a fairly simple example. But the idea here is you have that. You're always going to have a site plan for what you're looking at. You should be able to take that to scale, measure it up, and get an idea. Even if you don't have the full vertical, you should be able to look at that horizontal. And just like in this example here, as we look at the trees, does it present something that you can bring up to the developer and say, hey, we noticed an issue here. Can we make a couple of small adjustments? As long as everything's on paper, let's make a change now.
Right. And if I was a city engineer, I would likely write it into my policies, codes that I would want to see site distance checks as part of the development plan submittal package. But very few jurisdictions have that requirement.
That was our method one. Our second method involves going out to the site. And you can do this at existing driveways. You can do this at proposed driveways, even standing off the shoulder. Depends on if there's a ditch or not that can get in your way. But you can stand in the field and look each way and get an idea of what your site distance is.
Get out there with a measuring wheel, figure out about where the driveway will be, and get yourself in about the right location and basically sit in a lawn chair.
Pretty close, yeah.
And you can also do this, as Brian will show here, at existing intersections and neighborhoods. So this is the more real world example of how we're measuring existing site distance at existing locations on top of estimating proposed developments.
So for this example, or for what we do, you generally only need just a clipboard. You need to record some things, and then you need your stopwatch, because in this instance, we're not going to be measuring, we're going to be using the time factor. So in all those formulas, we talked about 7.5 seconds, which is what a passenger car needs in order to make that movement through an intersection. If we can record That's 7.5 seconds from when we see a vehicle to when it gets to the intersection. We have sufficient sight distance, and that works at any speeds, which is why I think this method is superior to measuring. Measuring, you're typically falling back on what's the design speed, what's the posted speed going to be. This method takes into account how people are driving. If they are speeding, you are accounting for that. If they are going slower, you are accounting for that. Whatever the circumstance is, you're looking for that time gap in this instance. So let's see if we can get this video working here. There the car came, and the red on the bottom is measuring that 7.5 seconds.
So we
It was
have,
a little rough, yeah.
yeah, but we have more than 10 seconds for sure there. You saw the 7.5 seconds on the bottom of the video. So we're in great shape there at this intersection. Again, approximately sighted back about 15 feet off of the intersection, roughly 3.5 feet up, and we're in great shape.
Yep. And now we go to a second example, a little more urban. You can see parked cars, lots of stuff going on, lots of poles. It could be in the way there, but as we're looking through, there comes the car. We got our timing on the bottom again. We're looking for that 7.5 seconds. And there's our 7.5, and there's the car. So we are right at the edge of our sight distance there.
So as engineers, being right at the edge always makes us nervous. So we obviously don't like that scenario. And tough situation here. Do we go to an all-way stop because there's limited sight distance? Do we man parking on one side? Do we scatter? Do we create a no parking zone up further, back up the intersection? These are the creative engineering solutions we have to bring to the table. But now we're aware of it. And obviously, I don't know that we explicitly said this at the beginning, but limited sight distance leads to safety problems. So we're being proactive here. And even if there isn't a crash problem today, we are being proactive on how we can enhance safety out there, especially if it's something as simple as moving a sign or trimming a hedge, that we want to get ahead of those things.
I'll also mention for this sight distance, for our site visit when we're going out to these places, we typically try to get at least 10 in each direction. Engineers, you want a big sample size, you try and get lots of measurements in there, you can take an average and go from there. And when you're getting on the edge like this, it can make a difference. If you have one that's on the edge and 9 others that are fine, you're probably sitting pretty good. All of them are on the edge, or some of them even under. Now we start looking at what else do we need to do in this situation. So don't just take one measurement, take a lot, make sure you're doing it right, and make sure you're getting down to even the tenths of seconds, because that does matter.
Yeah, very valid point. In a past webinar, we've talked about street audits. We feel every city should be doing on a rhythm, a routine basis. And this is one of these things that you could hire an intern, their summer work, part of it could be getting out to all the intersections and doing these checks, along with a host of other work. But because a lot of this is dependent on vegetation growing and changing and neighbors planting things, right, residents, it can't just be set it and forget it.
Exactly. So as we're starting to bump up against our time, we'll get some closing thoughts here. And number one is, if you're not doing it today, you should be including it as part of your typical traffic impact, transportation study. It should be routine. For a development, you should be looking at their driveways. Even corridor studies, you should be looking at that as part of it. And don't leave it for the reactionary safety study after the fact.
The second step is, yes, it's always great to check the plan set and go through the paper calculations. That's better than nothing. But we feel like the combo of getting the real world data as well as the plan set to account for how people are actually driving and what the obstructions really are out on the streets. Yeah, we prefer doing both methods.
Evaluate it early in your project. The earlier you do it, the easier it is to deal with, particularly if you're dealing with developers. Oftentimes, they don't get to the traffic study until the end. And so the earlier you can bring up these red flags and say, we need to do something, we need to move your monument, whatever it might be, the better it is for everybody.
Or even move the driveway 50 feet. And
Right.
that's why we would love to see cities codifying more in their processes, that traffic engineers are clearly capable of doing this, but the general site civils should also be capable of doing these calculations and showing it. And if it's a requirement, then it's early in the process. Deal with it when it's an early version of the plan and cheap to move the lines around.
We didn't talk about this one too much, but avoid too much sight distance. More is not always better. And we want to provide enough. We want to even provide that margin of safety so people can feel safe as they're making their turns, but we don't need to see 3 miles down the road. So don't feel the need that everything needs to be clear cut and take everything away. You need to have adequate sight distance, not miles on and miles.
Right, so if the speed limit is 25 miles an hour, well, make sure you're providing 300. If it's 30, well, 330 feet. But if you provide 500 feet with a 25 mile an hour speed limit, you're actually encouraging, you're nudging behavior and making it comfortable, and people drive to the comfortable speed.
Mhm. Always provide your recommendations to clear and maintain sight distance. So 2 clears in there. 1, be very clear in your recommendation, and 2, make part of your recommendation to maintain and keep clear sight distance.
Yes. And then, of course, if you're in an existing situation or for some reason a site plan is sacred, yes, we can look at adding more stop signs to change the control, roundabouts, lots of creative engineering options we could look at, but that's kind of putting the Band-Aid on, and that's not solving the issue. We would much rather solve the issue without resorting to traffic control, but it's part of our toolbox, so we need to keep that in mind.
Definitely. The last thing we've got for you is just, we talked about the side street stop case, but there is that no control case, which we argue is very good for the majority of your neighborhood streets, neighborhood intersections. And this really gets to the triangle of what you need as people are coming up to the intersection. They need to be able to see through that triangle to the other road.
But we're encouraging 10, 15 mile an hour speeds creeping through the intersection. We're not trying to provide a clear sight line for everyone to being able to go 30 miles an hour. So this is better than nothing. That we definitely recommend all of our city clients have something in their codes, policies, ordinances, wherever it makes sense, the way your system is set up, but have a minimal situation like this so you can have it documented, and when a resident goes and plants some shrubs, which happened to be in Maple Grove, and I could pull out the ordinance and say, I'm sorry, but you're breaking the rules, you gotta rip those shrubs out. It's a much more comfortable conversation than the resident saying, you're making stuff up on me.
Right. Always good to have something documented, gives you a starting point to go. So we have hit our 1 o'clock. We want to thank everybody for attending, but I know we've got some questions coming up, so we will stay on. We will answer the questions. For those who need to go, we appreciate you joining us. We hope to see you next month as well.
Yeah, you're always available. Go to spacconsulting.com and schedule a free consult if you want to talk to us. Yeah, so why don't we turn it over to Paul to go through some questions with us.
Absolutely. And I'm going to do you guys a favor and turn on the video.
You get to see Bryant and I, and this was not planned, but we're here in our SPAC consulting uniform of gray sport coat, white shirt.
It's hard to tell us apart when we do this.
Right. So we have quite a few questions. I'm just going to kind of go through a lot of these here. There seems to be a push in the community, Terry says, to put stop signs in all local residential intersections rather than allowing them to operate as a uncontrolled yield to the right intersections. Do you find this common in many cities around the US? Also, adding to that, many younger drivers don't seem to understand the concept of slow-looking yielding if necessary. They seem to just want stop signs. Do you have any thoughts on this trend?
Several.
And we touched on it a little bit already.
Yeah. Part of what we have done in our research is looking at compliance at stop signs, particularly ones at neighborhood streets. And if they're not warranted, if there's not a reason for those stop signs being out there, the non-compliance is staggering. I mean, we're talking 80%, 90% of the people are either rolling through, not stopping at all. Some of the videos we have are flat out scary of people just going right through a stop sign.
Yeah, where we're finding a quarter of the people going through the intersection don't even hit their brakes. And personal anecdote, when I was a very little kid, growing up in urban Minneapolis, we had stop sign on our corner. I was taught, look both ways, cars are gonna stop. And I almost got hit by a car as a 5-year-old because I was taught cars stopped. The car didn't stop. And luckily I was not into the intersection or anything like that, but we're setting up kind of a false system by just putting up a stop sign and assuming people follow it, because the data bears out it doesn't work that way.
Yeah, and it could be a legacy of the old basket and weave as well, which used to be a traffic calming thing of you put the stop sign on every other block, and of course people are going to stop, and it's magically going to slow people down through the intersection, which is also completely false based on what we've found. So there's lots of reasons for the stop sign. There could be a psychology thing too. People think it's going to be easier if they if it just tells them what to do, everybody will obey it. But we disagree with that, and we would much rather see you start with the uncontrolled, or be very sure you have a reason to put that stop sign in.
How did you arrive at the 1.47 factor? Is that a standard factor?
It's a conversion factor to take it from miles per hour to feet per second, and then when you do the rest of the multiplication, you get your distance factor. So it's
In feet.
Yeah, just standard conversion factor.
Yeah, so taking miles to feet and hours to seconds.
For V in the calculation, would it not be better to use a higher speed value than the posted speed limit, as that's common, say, especially in Florida, where I believe Howard is from, to drive over the speed limit?
This gets back to where we said we don't want to provide too much sight distance. If we provide a roadway that you could land an airplane on, people are going to drive faster. So it's people drive to the context. So this is kind of, we want to be Goldilocks here. We want to get it just right, of providing the right amount of sight distance for the behavior we're expecting out there. And if we provide sight distance for 20 miles an hour over the speed limit, we shouldn't be surprised if people are driving over the speed limit.
Okay. And I think this kind of goes into a little bit as well. For commercial driveway, is it common to increase the sight distance due to assuming trucks versus cars are waiting to turn, or is that part of that not wanting too much?
So our everything we presented was based on passenger cars, which is that 7.5 seconds. If we go to an industrial area, if we have more trucks that we're expecting, that's where that time factor would increase. There's slower acceleration with trucks. It takes more for them to move. And so that can increase to 9.5, 11.5. There's also different factors for grades in there too. If you're on a hill over a certain percentage, you want to add more time to it. So what we presented was a very basic case for your passenger car. If you want to get into those edge cases, please go back to the Green Book.
Yeah.
They've got those detailed in there, and they tell you how to change that conversion factor so you are looking at more time and adding it appropriately.
Yeah, we are doing engineering calculations as licensed engineers here. So we're definitely giving you the 80-20 solution. But But yeah, if you're in an industrial park, certainly do the more detailed calculations.
You presented a scenario where there's minimally 7.5 seconds of sight distance. This person appears that they saw a major street vehicle through a gap in the parked cars. Is that appropriate?
Keep in mind that these videos are pretty rough, just cell phone shot videos, nothing technical. So when you are out on the site, they actually looked a little better than what was shown in the video. Yes, you are correct though. If you have a line of cars, what does that mean in terms of your sight distance? And one thing I would have done if this were part of our study is I would have really looked at that factor of where does the driver stop. We need to go about 15 feet away from the edge of the travel way. As we were recording these, I think we were a little farther back, more than that, because we were behind the stop sign. With the parked cars there, we probably had room where we could have moved up a little bit. That may have changed the sight distance more.
Yeah, we can assume that the car, once it gets to the stop sign, if it can't see it, will creep up. And we can account for that creeping as long as it's safe, as long as they're not pulled into the travel way. So there's some nuance there.
I just want to give a time check for everyone. It is now 1:06. If some people have to get back to work or whatever, I just want to make that time check here. Agencies frequently allow on-street parking right up to the curb return, and this typically prevents achieving the necessary ISD. You may not even have SSD because of the parking. How do you discuss that with the agencies? Because typically they're attempting to maximize on-street parking because of the demand.
You may end up needing to go to an all-way stop condition because of that. If the on-street parking is more important than the sight distance, you have to start looking at alternate solutions.
We would start with pulling the parking back. Can we take one space out to improve that safety? That's always a starting point of how can we improve that? How can we improve that sight distance? And it's one space or maybe two spaces. What does that mean to the overall demand? And then as we start going down that road, that's where your study can lead to multiple different directions, including is it an actual demand or a perceived demand for parking? And if it is an actual demand, then we start looking at other options, always stop, other things we can do to try to make it better.
But you also need to note if we're in urban core with parking solid on both sides of the street, the traveling speed of those cars is going to be much lower because it's effective traffic calming. So maybe we're looking at a 10-mile-an-hour speed design instead of the 30 for the road. So that gets back to measuring the 7.5 seconds of what people are actually driving out there.
Someone wants a clarification question. They thought Green Book was 10 feet, not 14.5 feet for distance. Did that get updated or changed?
Pretty sure our current version, I don't know what the old versions are. The current version that we have, it talked about the 14.5 feet from the travel way. And that's an important distinction. I can't speculate what the 10 feet might have been an old version. I don't remember.
Yeah. Again, just go back and if you have any of these questions, double check your standards that apply. So please double check that.
Does the 85th percentile come in any of this?
I could, if you're looking at 10 to 100 cars and you're starting to do your spot and really get into the statistics.
Depends on if you're talking about speeds.
Yes,
If you're talking about the 85th percentile speed, that could be a good starting point for using the calculations and doing the measurements. Again, if you're just out in the field and you're doing measurements, I would hope that all the cars that you hit would give you that sight distance. But yeah, depending on your sample size, maybe it's okay with that, but you definitely need to go through, do all your measurements, do your calculations, justify what you're doing. So that everything we do needs that dose of engineering judgment with it as well.
It does, but I think we would be looking at, we for sure want 8 out of 10 vehicles to pass the 7.5 second sight distance. Our alarm bells are gonna be going off if we're below 8, 8 out of 10.
So we're at 10 minutes after 1. I'm going to give you guys one more questions, and then we'll get to the. If anyone has any more, they can email them. This is about the safety triangle. Is that necessary when already providing a sight distance triangle for the stop condition?
The sight distance triangle, the one we showed at the end, is closer to the no control, where there aren't stop signs out there, or yield control, where people can go right through without stopping. So there are two different cases there, and you need to be looking at your intersection and applying the correct sight distance for the correct case. If you have no control, look at those corner triangles. If you have a stop sign, you want your intersection sight distance in that 7.5 seconds.
Okay. Well, thanks everyone. Of course, feel free to reach out if you have any further questions. And next month, we're going to be doing an Ask the Experts session again of the Mike on Traffic webinar. So also feel free to email me, mspack@spackconsulting.com, with any questions you have related to transportation planning, traffic engineering, data collection, any of those good things. And we'll be back next month. Thanks, everyone.
All right, thank you.
Thank you, Mike. Brian, thank you everyone for showing up, and we'll see you next month.